Okay, so in today's video we're going to be having a look at circle sectors with trigonometry. Now we're going to start off with some relatively nice ones, okay, using a little bit of area of a triangle. So do obviously make sure that you check out some of the videos in the description to make sure that you're clued up with all of the trigonometric rules and formulas. Okay, but we're going to start off with some quite nice ones just using area of a triangle. We're going to move into some other questions that are going to involve a little bit more trigonometry, a little bit more thought process, a little bit of percentages. I'm going to have a finish on some pretty nasty questions with these where we might have to use sine rule, cosine rule, some SOHCAHTOA and some other little bits and bobs. So do make sure that you check out all of the trigonometry videos. Make sure that you're pretty clued up because I'm going to assume some knowledge across trigonometry with these topics, with these questions here, sorry. So we're going to get started with this one. So grab a piece of paper, grab a pen, make some notes, and we're going to kick start with this one question here. So I'm going to do this one first. Now I've got a couple for you to have a go at just to practice here what I would say is the basics. So that we are looking at grade 7 and above already just at the start of this topic. So obviously, you know, when I say the basics here, it's still a tricky topic already, but we're going to work out the area of this shaded segment here. And the segment just refers to, and I'll highlight it, this little shaded piece here that's created via the arc and the chord. That is the word there for what that little piece is called. It's called a segment. Okay, then what we're looking at is a circle sector. It says that PRS is an arc of a circle, and what we can see, the big full shape there is called a sector, and we're just going to work out that little piece. Now whenever it comes to a shaded shape, it doesn't matter how complex the question is, we need to work out the area of the full shape, which in this case is a sector, and then we need to take away the unshaded part, which in this case is a triangle. Okay, so first things first, we can work out the area of the sector. So I'm going to work this out in two steps. So I'm going to put sector over here. I'm going to work out the area of that. Now working out the area of a circle sector is quite nice and easy. You do need to know the area of a triangle, which hopefully you already know, which is pi r squared. So it's going to be pi r squared, and then we're going to times that by the fraction of the circle that we're looking at. So in this case here we've got 40 degrees. So we're looking at 40 degrees out of 360 degrees. There we go. And obviously that can simplify down, but there's no need to. So that's 40 out of 360. So if we plug all the numbers in there, let's obviously get rid of that radius because we've got the radius here. Let's put this in. So we've got pi multiplied by the radius squared. The radius in this case is 8 times 40 over 360. Okay, obviously we might only be given one of these lengths, but if we are, both of these are the radius of that circle there. So if I type that into the calculator, and obviously bear in mind these are all going to be calculator questions, let's see what we get for an answer. So pi times 8 squared times 40 over 360, I'm going to convert that into a decimal, and we get 22.3402. I'm not going to do any more decimal places there because it only wants it to 3 significant figures, and at the moment I've got it to 6 there, so we'll just keep that as it is. We could write down all the numbers if you want, but I'm absolutely happy just to leave it just like that. There we go, 22.3402 centimeters squared. Now I need to work out the area of this triangle here, and this is where our trigonometry is going to get involved because we're going to use our area of a triangle formula. There we go. So the area of a triangle is half AB sine C. Again, obviously check out that video in the description if you haven't, but let's actually work that out. So we've got a half, and then A and B are both the radiuses here, so A and B, and obviously our angle down here is our big C. So we've got half times 8 times 8 times sine 40. There we go, and obviously you could put 8 squared there. It's always going to be the same value of A and B as they're both going to be the radius. But let's just type that in. So 0.5 times 8 times 8 times sine 40. And there we go. That gives us an area for the triangle of 20.5692. There we go, 5692. Again, I'm just rounding that to 4 decimal places there. And again, that's an area, so that's centimetre squared. Right, there we go. So we've got the area of the sector, we've got the area of the triangle. So to get the area of that little bit that's left over and above the triangle, we just need to do the sector and take away the area of the triangle. So to finish this off, my last little bit of work in here will be 22.3402. I'm going to take away 20.5692. Right, there we go. Let's just type that in. So 22.3402. take away 20.5692. There we go, and that gives me a final answer of 1.771, which is 1.771. And obviously it wants my answer here to 3 significant figures, so we'll chop it after that second decimal place there, so it's 1.77. There you go, it's an area, so centimetres squared. And there we go, there's our final answer. That's how to work out the area of a shaded segment. Obviously a few different bits of maths there. We've got area of a circle, and obviously knowing how to apply that to a sector, timesing that by the fraction of the circle that we're looking at. And then we also had area of a triangle using sine there, and obviously just a little bit of logic here with how to work out a shaded segment, working out the area of the full shape, taking away the area of the unshaded shape. So it was a sector, take away the triangle. Right, let's have a look at some questions for you to have a go at then. Okay, so here's 2 questions for you to have a go at, so pause the video there, have a go, and we'll go over the answers in a sec. Right, okay, so for this first one on the left, now to work out the area of the sector, we're going to have to do pi times the radius squared. The radius is 80, so pi times 80 squared times 35 over 360. That's going to give us our answer. Let's have a look what we get for that. We get pi times 80 squared times 35 over 360, and that gives us 1954.77 if I round it to 2 decimal places. There we go. Once it's to 3 significant figures, again I've got it to 6, so that'll be fine. Then we've got to get the area of the triangle. So we've got half times a times b, so I'm just going to put 80 squared, a times b, just to save a bit of space, times sine 35. There we go, times sine 35. So we've got 0.5 times 80 squared times sine 35. Pressing equals, that gives us 1835.44 if I round that to 2 decimal places. Right, now we just need to take those away from each other, so 1954.77 take away 1835.44, all on the calculator, and that gives me 119.33. There we are, 119.33, and again it wants it to 3 significant figures, so we'll chop it after the 9, and that is 119 units metre squared. There we go, and that is the area of the shaded segment on that particular question. Moving on to the one on the right, same process. We've got pi times 10.4 squared times 120 over 360. And let's see what we get for that. So pi times 10.4 squared times 120 over 360. There we go, and that gives us 113.26. 113.26. Then looking at the area of the triangle, let's have a look again. So we've got a half times a times b, so times 10.4 times 10.4, I'll just put 10.4 squared again, times sine 120. There we go, let's work that out. 0.5 times 10.4 squared times sine 120. Pressing equals, and that gives me 46.83. There we go, let's take those away from each other and see what we get. So 113.26 take away 46.83, and I get the answer 66.43. So there we go, so 66.43. Again, it wants it to 3 significant figures, so that's 66.4 centimetres squared. And there we go, there's our final answer for that. Right, there we go. So in terms of actually just, again, basic, although these aren't that basic, again, but just in terms of basic shaded segments, that is sort of as far as you really need to go with the basic questions. We're going to start having a look at some of the slightly harder ones now with a little bit more thought process, and some of these kind of nastier exam questions that seem to be coming up. Let's have a look at those. Right, okay, so here's a question. I'm going to do this one question, then I've got a similar-ish sort of question for you to have a go at. But it says ONQ is a sector of a circle with centre 0, radius 11. Now there's no numbers on this diagram, so I'm actually going to put that on myself. So the radius here is 11 centimetres, there we go. Then it says it's an equilateral triangle, side length 7. So it says that word equilateral triangle, that gives us a nice little hint here to put this angle in as 60. Obviously angles in an equilateral are 60 degrees each. And then it tells us the radius, or not, sorry, not the radius, so that the side length for that is 7. So there we go, that's 7 centimetres right there. And it says calculate the area of the shaded region, as a percentage of the area of the sector, and give your answer correct to 1 decimal place. Right, okay, so we'll have a look at this. So we need to get the area of the shaded region, and we need the area of the sector. So first of all, we can get the area of the sector. Let's keep this all nice and tidy. So we'll label this up. We've got the sector. And to get the area of the sector, we're going to do pi r squared, the radius is 11, so pi times 11 squared, times by 60 over 360. There we go, 60 out of 360 for that circle sector. So pi r squared, so we've got pi times 11 squared times 60 over 360. And that gives us a final answer of 63.355. Let's have a look. So 63.355. It wants my answer to one decimal place, so I'm going to leave them all to at least 3. Right, there's the sector. So now let's work out the area of the triangle, and then we can get the area of the shaded section. So for the triangle, and we'll label all this up again. So the triangle, we need to do half AB sine C. So we've got half times A, which is 7. Again, the other side's 7 as it's an equilateral, so that's going to be 7 as well, times sine 60. There you go, very similar to before, but obviously that triangle isn't extending all the way up to the circumference, but that's fine, as long as we can get the area of that triangle, which we can, as it's given us the length. Obviously it's not the same as the radius this time, because it's given us an actual length of that triangle, but obviously we're just following the same process here, so 0.5 times 7 times 7 times sine 60. There we go, and that gives us an answer of 21.2176, so 218 if we keep it to 3 decimal places, so 21.218. There we go, that is the area of the triangle. Now let's get the area of the shaded part. There we go, so shaded, I'm just going to label that as. So to get the area of the shaded, we're going to do the sector again, 63.355. Take away the area of the triangle, 21.218. There we go, and that leaves us with a final area of 63.355. Subtract 21.218. That gives us a final area of 42.137. There we go, so 42.137. There we go, so that's the shaded area there. We've got the triangle there, and we've got the sector there. Just following all the same steps as those previous questions. Now it says calculate the area of the shaded region as a percentage of the area of the sector. So we've got the shaded region, 42.137, and that is out of the area of the sector, and the area of the sector is 63.355. There we go. So as a fraction of the area, it's 42.137 out of 63.355. So if I just type that into the calculator, 42.137 divided by 63.355. There you go, and it gives me a decimal, which is 0.665.09, so let's round that to a 1, and obviously there we can turn that straight into a percentage. So once you've got it like that, we can just turn that into a percentage by timesing it by 100, and we get a final answer here of 66.51%, but obviously the question wants it to one decimal place, so we're just going to have that as 66.5. There you go, percent, and that is what percentage is shaded within this sector. Okay, there we go. So an extra little step there, thinking about percentage at the end. But obviously when it asks for a percentage, you just find the actual area of the bit that it wants as a percentage out of the area of the bit that it's looking for you to actually say. And obviously I've highlighted those down there. So we had the area of the shaded region out of the area of the sector. So 1 divided by the other, times it by 100, and there you go, you've got it as a percentage. Right, so I've got one like this for you to have a go at. It is obviously slightly different to this one, but here's that one for you to have a go at. Let's have a look. Okay, so this question, very, very similar, but have a go, pause the video there, see what you can get, and we'll go over the answer in a sec. Right, okay, so it says, right down the bottom there, it says, work out what percentage of the area of the circle is shaded. So it wants the shaded part, so let's write this out. It wants the shaded, I'm just going to write that as shaded, out of the whole circle. Okay, there we go, whole circle. There we are, so that's what we're looking for right at the end, the shaded part out of the whole circle. So if we start to work out some of the bits here, and let's see what we've got. Now we've got the sector, obviously, so we can work that out again. So the sector, we are going to do pi times 30 squared, the radius squared, times 80 out of 360. There we are, so let's see what we get for that. So pi times 30 squared times 80 out of 360. And that gives me a nice decimal here, 628 points. Let's see, how did it say, what says what percentage of it is shaded? So nothing about rounding or anything here, so 3185. I'm just going to round it as appropriate. Let's have a look. So I'll keep to 4 decimal places for the moment. So there's the area of my sector. Now let's have a look at the area of the triangle. Right, so half AB sine C, so it's a half times 30 times 30, so 30 squared times sine 80. So what we get for that, so 0.5 times 30 squared times sine 80, and that gives me 443.1635 if I round it to 4 decimal places. 0.1635, there we go, and there's the area of the triangle. Now obviously we can get the area of the shaded part, we can take these away from each other. So the shaded part is going to be 628.3185, take away the triangle there, which was 443.1635, take those away, let's see what we get. So 628.3185, take away 443.1635. There we are, so we get an answer of 185.155. So 185.155. Right, there we go. So that is the area that's shaded. Let's just label that up. Shaded. There we are. So that's the first piece that we need. We've got the shaded part, which is on top there. And we want to do that out of the area of the whole circle. So we can get the area of the whole circle. We just need to do pi r squared. And we've already actually done that. We've just done, we've also, there we are. I'll just underline it. There we are. Pi times 30 squared. So pi times 30 squared. And what does that give us? Let's have a look. Pi times 30 squared gives us 900 pi, or a decimal here, which is 2,827.4334. 4334, there we go, and that is the area of the circle. Let's just highlight this up as well. So there's the area of the circle, which is the whole circle down the bottom there. So now we can just plug those both into the fraction. Let's have a look. So we've got the shaded area, which is 185.155, and that's out of 2,827.433. There we go, and let's type that in and see what we get. 185.155 divided by 2827.4334. There we go, and let's have a look. That gives us 0.065485. Let's have a look. There we go. Right, so turning that back into a percentage, we'll times that by 100. Obviously that's in decimal form at the moment, so times it by 100, let's see what we get. We get 6.55 if I round it to 2 decimal places. There we go, so 6.548 or 6.55. There we go, what percentage of it is shaded? Well, it's 6.55%, and that's going to be rounded there. Now this question doesn't say how to round it, so I'm just going to write 2 decimal places there, just to show how I've rounded it, but there we go, 6.55. When it comes to an exam question, obviously if it doesn't say how to round it, you don't round it at all, you would just leave all the numbers in there. So for this question I would have actually written 6.548518.526%, which would be absolutely ridiculous. There we go. So normally a question would say how to round it, so but this one just happened to not have any any rounding criteria with this particular question. So there we go, I've done it to 2 decimal places. 6.55% of the circle is shaded. Right, let's have a look at another type of question then. Right, okay, now we are coming towards the end of these sorts of questions. I've got 4 more to have a look at with you, all just things that are just a little bit different, more exam style questions. So we're going to have a little look at these. I would suggest maybe with these next couple of questions to sort of pause the video, have a go, see what you get, and obviously just see then follow through if you're not sure. But I've picked out some quite well-known exam questions that have been coming up recently, some sort of slightly different ones that could be coming up on the exams, you never know. But I've just tried to find a little selection of different sorts of questions. I have got one specifically for you to have a go at in a sec, which is another pretty tough one as well. But I've got 4 questions now we're going to have a look at, so we're going to kick it off with this question here. Now this question says, work out the length of the arc ABC. Okay, and it gives us some information. It says that the length D to O is 9 and that these are tangents to the circle. So we've got a lot of different bits of maths going on in here. So we need to just have a look at this. Now the first line says that it's a circle radius 5. That's given to us on the diagram just there, so we don't need to worry about that. The next thing is it says that DA and DC are tangents. Now a tangent meets a radius at 90, so we can put some right angles in here. Obviously there where the radius meets the tangent. So as you can probably see, we've got some right angled triangles, so it may be that we can use some SOHCAHTOA on these. Now the next thing that we're told is that the length DO is 9 centimetres. So we can stick that on the diagram as well. We've got 9 centimetres here for the length D to O. And then it wants us to work out the length of the arc ABC. So let's highlight that, A to B to C, and there is that. Okay, so the next step now is to think how we're going to get to this actual answer, because obviously we've put all the information onto the diagram. We just need to have a think about how we now might approach this. So we're trying to work out the length of that big arc. Now what we could do is we could think, well, actually we can work out the length of the full circumference of the circle. So if we can get the length of the little arc here, we could just take that away from the full circumference of the circle. We could do that. That's one way we could have sort of approached this, or potentially maybe we could find out what this angle is here and then just do the full circumference and times it by the fraction of the circle. Lots of different ways that we can think about approaching this. I'm not really too sure how I'm going to do it as I get there, but let's just have a look and see sort of where this goes. So for the starters, we need to get some angles. Okay, we need an angle within the sector. We've got these sort of sectors that are getting created here. I'm just going to draw it in. We've got this sector here. There we go. Or we could actually just look at that as one big sector. This one here, I'm not drawing that in very well, but there we go. There's a big sector there as well. So if we can get these angles here, okay, then we're going to be able to work out the arc length of that sector. So let's just have a look. So we've got this triangle here, and we've got two of the lengths. Now we can use Tutor to work out an angle as they're right angled. We can actually work out this angle just here. So if I label this triangle up, look, we don't need the opposite here, but we've got our adjacent and we've got our hypotenuse. So we can use cos, okay, and those of you that use formula triangles, again, there we go. CAH, when we want to work out the angle, we're going to do cos minus 1, A over H, A is 5, H is 9, so cos minus 1, 5 over 9. There we go. So let's type that in, cos minus 1, 5 over 9, and that equals 56.25 degrees. So there we go, 56.25 degrees. Now that's going to be the same for the one above as well, so we can just label both of those. So let's just times that by 2. We could just write 56.25 in both of these if you want. 56.25 and 56.25. But there we go, let's just times that by 2. And that gives us 112.5. There we go, so 112.5 degrees. Now that's completely up to you now whether we work out the length of the small arc and take it away from the full one. I actually think just looking at this, it's probably easier now for me to just work out this reflex angle here. So let's take that away from 360 and get the length or the size of that angle just there. There we go. So 360, take away 112.5. That is not 112.5. So write that in again, 112.5. There we go. And what does that give us? 360, take away 112.5, and that is 247.5 degrees. There we go, 247.5 degrees. Now we've got the angle in that major sector, the big sector. Okay, so actually if I get rid of all of this sort of writing for the moment, and let's just write that angle in here, 247.5, we can now use the large sector, which we call the major sector, to work out the length of this arc just here. And we can do that just like we've done with areas as well. We could actually just do our formula for the circumference, which is pi times the diameter, or pi times 2 times radius. I'm just going to do pi times diameter, or 2 times the radius, which is 10, so pi times 10. And then we're going to times it by the fraction of the circle we're looking at, as we're just straight away looking for that major arc. It's just going to be 247.5 out of the total 360 degrees. There we go, so pi times 10. And let's type this into the calculator, pi times 10 times and then fraction, 247.5 divided by 360, and that gives us 21.598. There we go. I have rounded that to 3 decimal places there, centimetres, but it wants my answer to 3 significant figures, so that would be 21 point, chop it after the 5, and that's going to be 6, so 21.6 centimetres. There we go, and there's our final answer for that question there. So lots going on in that question, different ways of approaching it. This time we had a bit of Tutor to use just to work out some lengths. Okay, obviously we could be thinking about using the sine rule or the cosine rule at some point if it was non-right angled triangles, or even sometimes when it is right angled triangles you can still use the sine rule. But then we used that to find out the angle in the major sector, and then obviously used our circumference of a circle formula just to work out the length of that arc there. Okay, so it does say the length of the arc A to B to C. Remember, A is here, B is over here, C is there, so it's indicating there that it is the larger arc there, or the major arc there, that you actually want to be looking at. Right, let's have a look at another type of question. Okay, so this question says APB is an arc of a circle centre 0. The area of the sector is 5 pi centimetres squared. calculate the area of the perimeter, calculate the perimeter of the shaded segment and give your answer to 3 significant figures. So to work out the area, the perimeter of the shaded segment, we're going to first need to find this length here, and then once we've got that, we're also going to have to find this length here. Okay, so we've got a couple that we're going to have to be looking at. Now we can get the length once we know what this angle is. Okay, and that's where it's given us this extra piece of information this time. It's said that the area of that sector is 5 pi centimetre squared. So we can actually work backwards from this. So to get the area of that sector there, we would do pi times the radius squared, so times 6 squared, times by the angle, let's call it x, out of 360, and it's then the answer to that is 5 pi. There we go. So all we need to do is rearrange this. So let's divide both sides by this bit here, which is 36 pi. So we would have x over 360 equals 5 pi over the 36 pi there. 6 squared is 36 times pi is 36 pi. There we go. So we've got that. Now to get x on its own, we'll just want to times both sides by 360. There we go. Obviously you can type these all in on the calculator, but I just want to times by 360. And that's going to give me my value of x, which is my angle. So let's type that in. We've got 5 over 36 pi, 5 pi over 36 pi, and then we're going to times that by 360, and that gives us a perfect answer there of 50. There we go. Obviously, if you'd have rounded those to decimals, you might not have got perfect on 50 here. So if you can leave it in terms of pi, leave it in terms of pi. But there we go. We've got 50 degrees there. Let's write that in, 50 degrees. Right, now we can use that to work out the length of the arc to start with. I can find arc length. I can do pi times the diameter, which is 2 of those 6's, so 12. And then times what fraction of the circle we're looking at, which is 50 out of 360. There we are, so pi times 12 times 50 over 360, let's see what we get for that. Pi times 12 times 50 over 360, and that gives me 5/3 pi, or 5.235, let's have a look, 3 significant figures, let's keep it to 4, so 236, 5.236 centimetres, there we go. Moving on to the next bit, we need to work out the length of this, A to B, to get the perimeter of that shaded segment. Obviously we've got the arc length now, so let's have a look at working out the perimeter. Now how are we going to get that? That's the question. Now, we've got a triangle there. It's a non-right angled triangle, so we could think about using the sine or the cosine rule. So let's have a look. Now we could work out these angles here and then use the sine rule. That's one way of doing it, okay, obviously because that's an isosceles triangle. Obviously with the 2 radiuses there both being 6, we've got the top angle of 50. So we could take that away from 180, get the base angles and use a bit of sine rule if you prefer the sine rule. Or actually, let's have a look, we could work that out because it's opposite this angle and we have these 2 adjacent sides here, so we could just use the cosine rule. So let's call that A, and big A, and then little b and little c. There we go, so a squared equals b squared plus c squared, so 6 squared plus 6 squared minus 2bc cos a. There we go, obviously there's your cosine rule as well. So 2 times 6 times 6 cos 50. Just about fit that in, there we go. Right, so let's type all that into the calculator. So 6 squared plus 6 squared minus 2 times 6 times 6 times cos 60. Cos 50, sorry, why am I typing in 64? Cos 50. There we go, and that gives us an answer here. So we've got a squared equals 25.719. There we go, so square root that for a, and we get a equals 5.071. There we go. Right, okay, so that gives us our length of A to B. So we've got our 2 lengths that we need now. We've got 5.236, which is the length of the arc, 5.071 using the cosine rule to get the length of A to B, and then we can add those together to get the full perimeter, and let's just write that down here. So 5.236 plus 5.071, and that gives me a final answer. Let's type this in, 5.236 plus 5.071, and that's 10.307. 10.307 0.07. Now it wants the answer to three significant figures again, so let's have a look. Let's just write this down over here. So it would be 10 point and then 3. There we go, centimetres. Obviously there's a 0 after the 3, so it just becomes 10.3 there to three significant figures. Right, and there's our final answer for this question. Right, okay, we've got two more to have a look at. This next one's quite a tricky one, so I'm going to flick to that now for you to have a look at it. Okay, so this question here. Now, I would say have a little go, pause the video, see what you can make of this. Think of all the different techniques that we've been looking at with area of a triangle, and potentially using sine or cosine rule. Thinking about any of those sorts of elements with the isosceles triangles or equilateral triangles and all the sort of stuff we've looked through in this video. This is a very, very difficult question, I would say. But pause the video there, have a go, see which bits you can work out, see how far you can get through it, and we'll go over the answer in a sec. Right, okay, so it says, the diagram shows a regular pentagon inside a circle. TA is a tangent to the circle, and OBT is a straight line. Work out the area of the triangle ABT and give it to three significant figures. So ABT is this triangle here. Now, there's no maths in this that we haven't already looked at, so let's just have a look and see what we make of it. Oh, obviously that triangle is shaded in, so let's get rid of that highlighting. Now it says that there's a regular pentagon inside this circle. Now a regular pentagon is obviously made up of 5 triangles. There we go. Now, all around the circle, or all around the inside of the circle there, we've got 5 angles making up 360. And if we do 360 divided by 5, we get an angle of 72 degrees. There we go. So we know that in that little sector there, we've got an angle of 72. So this is the sector that I'm looking at right now. And I'm just thinking, what can we do in terms of maths that we already know here? So we've got the angle 72, and we've got both of the radiuses there are 7. So we could potentially be looking at finding this length just here within the on that triangle there. So there's one thing that we can start with, just to find that length. Obviously, in order to work out the area of the triangle, we need a couple of lengths and an angle. Obviously, half AB sine C, we need the angles that are adjacent, sorry, the sides that are adjacent to the angle that we're using. So let's just do this maths here and see if we can figure that one out. So we can use the cosine rule for that again, just like the last question we looked at. So that's opposite the 72, so this would be my big A. So we could do A squared equals 7 squared plus 7 squared, b squared plus c squared, minus 2bc, so 2 times 7 cos 72. There we go, so let's just see what we get here. So working that out, so we've got 7 squared plus 7 squared minus 2 times 7 times cos 72, and that gives us 67.716. 67 point, I'm just going to put 72 because I'm going to square root that anyway for A. So A equals the square root of that, and we get 8.229. There we go, 8.229. I'm going to leave that to 4 significant figures there, and that's in centimetres. So we've got that length there, so let's get rid of some of this. There we are. So we can label that up. That is 8.229. There we go. Right, okay, so that's just the first thing that I've spotted just from the fact that it said that there was a regular pentagon there, and obviously just thinking about the actual triangles within it. Now let's have a look at the next bit of information that we've got. So we've got TA is a tangent to the circle. So I'm just working through this information line by line. So TA is a tangent to the circle. So if that's a tangent to the circle, let's have a look. We've got a right angle being formed with the radius. There we go. So whether that's going to help me out or not, I don't know. But we've got a right angle there. What could we actually work out from that? Now let's have a look. We've got this big right angled triangle. There we go, we've got a right angled triangle, and now we actually know one of the angles, and we've only got one of the lengths there. We've got the 7 on the left, so we can't actually go any further, but we could work out this bottom angle in the triangle here, because we've got the 72, we've got the 90, so actually we can definitely work that one out. We've got 180, take away 90, take away the 72, and that's going to leave us with 18 degrees. There we go, so that's 18 degrees. Whether we need that or not, I'm not really too sure at the moment, but there we go, there's the working out for that. Let's just get rid of that and get rid of this, and just, there we go, there's the next piece of information. That's just something I've managed to get using that, obviously, that piece of information at the tangent to the circle there. So we've got that. Now can we work out any other further lengths? Let's have a think. We could actually work something out now. I'm just trying to think how we could go about this. We could use a bit of the sine rule to work this one out potentially down here, this length of the bottom part of the triangle. Yeah, we could actually do that. Maybe we should do that. Okay, we could have done that already using SOHCAHTOA, but again, you could use the sine rule here if you wanted. Now, let's have a look. So, using that angle of 72, I'm going to swap to a different colour here. So, opposite the 72 is the x. Obviously, we could use the 18, but I'm just going to stick with what we had originally because I didn't really need the 18, but there we go. Just something I could have found with that bit of information. So, we've got the opposite. 7 is the adjacent, and the angle that I'm going to be using is 72. So opposite and adjacent, that's going to be tan, and again I'm going to use a formula triangle for this, so TOA, there we go. So to work out the opposite, obviously we do a multiplication there. So the opposite is adjacent 7. Let's have a look, where shall I write this? There we go, 7 times tan 72. There you go, the angle that I'm using. So 7 times tan 72. And that gives me 21.54. I'm going to write that in down there. Let's just get rid of all this working out now so I can write that in properly. There we go. So that's 21.544. If I keep it to 3 decimal places, what did I keep the other one to? Yeah, 3 decimal places. So 21.544. I'll round up that 3rd decimal place there because it's a 7 after the 4. So 21.544. Right, let's have a look and see where we can go now. Get rid of that. There we go. Right, so looking within the triangle that we're actually looking at. Hold on, let's see if we can get rid of that. There we go. So within the triangle that we're looking at now, we're looking at this shaded triangle. I've got one of the angles over there, which is 18. I haven't got any of the other angles within the triangle yet, but I have got those 2 there. Now I'm just thinking, and there might be other ways of looking at this, but I've got this length and I've got this length. So if I can find this angle in between it, then I will be able to use half AB sine C, okay, because I've got those 2 lengths. Now we might be able to do this in other ways, but I'm just thinking actually, I think I've spotted a way to find that angle that I think might be useful. So actually looking at the fact that there's a right angle in that triangle, so let's just get rid of this for a second, just talk about this next bit. I didn't want to get rid of that as well. There we go, just that bit. Right, so given that this is a right angle, look, I can actually look at this angle and this angle in the triangle there, because I know we've already mentioned right at the start that that's an isosceles. And I can get the base angles there because the top is 72. So I can get this part of the angle here. So I do 180, take away 72, we get 108. I'm just going to write this down. 180, take away 72 is 108. And then we can divide that by 2. And that'll give us 54 degrees. There we go. So the base of both these base angles in this isosceles here are 54. And as we know, it's a right angle. Let's just work this out. There we go. We've got a total right angle there. Part of it is 54. So 90 take away 54 is going to leave us with 36 in this angle here. There we go. And now I've got that 36, I can actually go about working out the area of this triangle. So let's just get rid of this for a sec. Let's move that over there. All the working out we've done. Right, so just looking at this as a completely separate, I've sort of drawn all over this now, but the separate triangle we're looking at, we've got a triangle. We've got that this length is 8.229. We've got the angle down here is 36. And we've got this bottom length is 21.544. So I've got all the lengths and pieces that I need to use half AB sine C. Okay, I've got the 2 sides that are adjacent to that angle. So let's just go about actually working this out then. So I've got a half times 8.229 times 21.544 times sine 36. There we go. And let's type that all in and see what we get. Right, so 0.5 times 8.229 times 21.544 times sine 36. There we go, and that gives me a final answer here of 52.102 or 103. Keep that rounding it properly. And it wanted to 3 significant figures, so that would be 52.1. There we go. And what we're working out? We're working out the area, aren't we? So it's centimetre squared. There we are. So 52.1 centimetre squared. Final answer. There we go. That was obviously a pretty mad question there. There's a lot going on. You couldn't really get a question much harder than that, I don't think. I think that's probably one of the hardest ones I've seen on this topic. So thinking about what we actually used there, we used the cosine rule initially to get one of the lengths. Then we had to sort of think outside the box with the big right angled triangle, knowing obviously the tangent to the radius was 90 and spotting that we could use SOHCAHTOA or the sine rule there. Obviously then working out one of the lengths and figuring out which ones we actually needed. We got the 21.544 down the bottom. And then obviously just using a bit of angle rules with the 90-degree angle to work out that one. I think another route we could have gone, just thinking about getting rid of some of this working out. So if I get rid of some of this, let's have a look, we could have, let's just get rid of all of that. There we go. Once we got that this one here was 54, we could have potentially also looked at this angle here and maybe use some of the, maybe rather than working out this one down the bottom, we could have worked out this one here, and then we could have used these two sides here with the angle there sitting underneath the B. So just another way you could do it. You'd still get the same answer, but it's just another route that you could have taken. And I quite like that you can take two routes. Or to be honest, once you've got that X there that I've labelled, you could have used X and the one down the bottom. That would probably require the most working out because we'd used quite a lot of trigonometry to work out both those lengths. But there are actually probably three different ways that we could go about finding the answer there, which I quite like about this question. But there we go, let's get rid of some of that. That was quite a long question, but there we go, there's your answer, 52.1. And obviously if you're not sure on some of the steps there, you can always go back, have another look and run through that again. But I'm going to go over one more question now before we finish. Right, okay, so this is also one of the hardest questions that I've seen on this particular topic as well. It says OAC is a sector of a circle. Okay, which we've got there, we can see that sector. And it says that has a radius of 10, that's given to us. There we go, on the diagram, this is also 10 then, we can put that on. BA is a tangent to the circle. BA is a tangent to the circle, okay, right, so we've got a right angle. BC is a tangent to the circle, okay, so we've got another right angle. Angle AOC is 120, that's given to us on the diagram. Calculate the area of the shaded region and give it correct to three significant figures. Now straight away, and I think this is probably one of the harder bits to spot, is that obviously with the right angles there, if we can chop this in half, we've got two right angled triangles. Now if we can work out the area of those triangles, then obviously thinking about the concept of shaded regions, then we can probably get rid of the unshaded sector away from the full drawing there. So I'm just going to get rid of that. This is the last question. So pause the video there, have a go, see if you can get the work, sort of all the working out and some of the concepts that I've just talked about there, and we'll go over the answer in a sec. Right, okay, so splitting this up then, we get two right angled triangles, and that means this angle here is going to be 60 because we split that 120 in half, and the top angle up here is going to be 30. Now we want to get the area of that triangle, so in order to get the area of that triangle we need the length which is perpendicular to the base there, and if we look at the base being 10, we're going to need this height here which is perpendicular to that base. So we can use SOHCAHTOA to do so, it doesn't matter which angle we use, I could use the 60, so if we use the 60 we've got the opposite and we've got the adjacent, so I'm going to use tan for that. There we go, we're trying to work out the opposite, so I'm going to do t times a or tan times a, or 10 times tan 60. There we go, so 10 times tan 60, let's just type that in, 10 times tan 60, and again you might have taken a slightly different route here, but you should still get the same answer. You get the answer for the area of that triangle, the height of that triangle being 17.32, and let's see, it wants it to three significant figures, there we go, I'll leave it to 4 then. Right, so we'll get rid of this, we've now got that length, so we can get rid of all of that, and this here is 17.32. Right, so we can work out the area of this triangle now. So for step 2 here, I can get the area of this triangle. I can do base times height divided by 2, or half base times height. There we go, let's just write that in, half base times height. So half of 10 is 5, times the height, which is 17.32. So 5 times 17.32. There we go, and that gives us an area of 86.6. There we go, that's meters squared. Now obviously we've got two of these triangles, we've got one here, number 2 there, so I'm going to need to double that. That's going to give me the total area of the total shape, so double that, so times that by 2, and we get 173.2, so the total area there of the whole shape is 173.2 meters squared. Right, there we go. So number 2, we need to find out the area of the sector. So moving on to the sector, and let's keep this all labelled, so the sector here, we can work out quite nice and easy. We've got pi r squared times 120 over 360. There we go. So we just need to plug obviously our radius into that. So our radius is 10. So let's get rid of that. We'll put 10 in there. Pi times 10 squared times 120 over 360. So pi times 10 squared, there we go, times 120 over 360, there we go, and that gives us a final answer for the area of the sector of 104, and that's 0.719, so I'm just going to keep that as 0.7, there we go. That's obviously to 4 significant figures there, once the answer to 3, so 104.7 metres squared, there we are. Right, so to finish this off, obviously we've got the area of the whole shape, 173.2, which we've obviously found by doing 2 right-angled triangles, getting the area of one and doubling it. Now we've got the area of the sector down here, which is the unshaded part in this particular question. So to get the area of the shaded part, we need to take them away from each other. So we've got 173.2, take away 104.7. And let's see what we get, 173.2, take away 104.7, and that gives me a final answer of 68.5 metres squared. There we go, and because of the way that I rounded there, that's already come out as 3 significant figures. So 68.5 metres squared is our final answer. Right, there we go. And that is the very last question. That's the end of circle sectors and trigonometry. There's a massive sort of array of questions there on different types of questions with circle sectors and trigonometry, so there's a lot to go through. Obviously it'd be worth, if you struggled with any of them, obviously going back and having another look through some of them and maybe going through them again, but that is the end of the video. Obviously make sure you check out some of the further trigonometry in the description, which I'll have linked below. But there we go, that's the end. If it was helpful, it was useful, please like, please comment, please subscribe, and I'll see you for the next one.